All right, everybody. Thank you so much for joining. So, just to give you a little bit of context, usually when we do these reading groups, we select like a research paper and we invite our wonderful speakers to dissect it and dive a little bit deeper into it and see what's in there. But this time, we're not really covering a paper. Instead, we asked the community what they think were the most consequential things that happened in AI last year. And we got a bunch of responses. And based on those responses, we selected a few of them. And helping us go through all of them are our wonderful speakers, as usual. We have Adam, the founder of Head On, Sophia, she's a data scientist at Breckenridge Capital. We have Nehil, who is a member of the technical staff at Anyscale. We have Rohan. He's a staff senior engineer, staff software engineer platforms at Evolution IQ. And we have Sonam, who's a developer advocate at Tellings. And we have Lucas, who's a senior AI engineer at Stone. He's joining us for the very first time. Thank you, Lucas. And also we have Anna Yoon, who is a member of technical staff at OpenAI. So thank you guys so much for joining and helping us go through these developments. And just so you know, just to make it a little bit easier for us to go through these developments, we classified them into three clusters, right? Just to make it easier for the flow. So the first cluster is architecting and designing AI native workflows. And as you can see, we got agents, memory, context engineering, MCP, and evals and vibe coding in it. And then this is cluster two. We'll go through each of these individually. I'm just giving you a very high level background on what we're about to cover. The second cluster is multi-agent orchestration and model cognition, and this is cluster three. So evals, metrics, and open source. So without further ado, I think I've taken enough time. I'm gonna hand over to cluster number one, which will be covered by Rohan, Sonam, and Sophia. All right, guys, take it away.
Thank you, Benoy. So many thanks to everybody who joined. And I am going to talk about the agents because that's one of my favorite topics to talk about these days. I'm going to quickly share my screen and going to share. One second. Where's my little bird? There we go. Okay. Can everybody see my screen?
All good.
Okay, perfect. All right. So so the first topic I want to talk about is AI agent about from experiment to production ship. Now, in the past couple of years, we have heard a ton about agents, AI agents. In the last year, when I was talking about agents, the common question I used to get is, what is an AI agent? And the best answer I could come up with for that is that think about LLM as the brain. You have access to tools, the agent gets access to the tools, and combined the brain, which is LLMs, and the tools, it behaves autonomously. It could make some decisions on your behalf, and that's what your AI agent is. Now, from the last year to this year, I was wondering, like, how did agents leave the lab? So it's, just from the models became systems. Just from basic prompt engineering, those became workflows. From stateless calls, it became long-running groups. And it's basically all these like production going to into the production state. It didn't really just happen because models got smarter. And when I say that, okay, it happened with because we wrapped models with control, tools, memory, and even guardrails, which is, by the way, a very important component in agents. And agents became orchestrated systems, not just the APIs that you call once. So that's where it became more than demos, and it became a lot more involved in your daily work. And agents are not really equal, like, not really just one pattern. You have, we have task agents, you have conversational agents, multimodal agents, which is now the talk of the town. We also have background agents to do some monitoring, triage, automation, and so on. So this is where, like, when I talk about multimodality, I think about voice, audio, voice, image, videos, and of course, we have text. And all these, like, text agents are quite different from the other modalities agents. We have also been seeing a lot more coding agents, coming up, which I'll give you some examples in the later slide, they behave a lot more differently from operational agent or healthcare agent. So what I'm trying to say is that there is not just one architecture. The base stays the same where we have the LLMs, we have access to the tools, but then how it's all orchestrated, it differs based on the use case and the how much you want to scale. Now, why does one think that production agents are harder than demos? And I can say this from my personal experience. I do the lots of different demo, like prototype agents, but then when I see the engineering team taking those agents, pushing it into production, there's so much to handle. There are conversations that could last minutes, not just milliseconds. Um, Even when on the demos, it may work perfectly with, if you think about from the memory point of view or the state of that agent, because they need to persist correctly. And even like a small failure, it's not just retries, it needs like a strong recovery. And this is why, like, and at the end of the day, you also need to explain like why explainability becomes a requirement, not just like a nice to have. And all of this, I believe that latency matters and consistency matters as well. And one more thing is that the memory bugs are so much worse than the model bugs because it can create some many not just distractions but also like problems, especially if you are in I don't know, if it's a sensitive agent, a sensitive industry, for example healthcare. Now, I work at a company called Telnex, and we are in voice agent space. Now, so some of the real world examples that we have not only just built the demos for our healthcare customers, but we have been pushing these agents into production for them. For example, just recently I had given a demo on symptom triage nurse agent where I wrote a very comprehensive prompt to the agent, selected different LLM transcription models, speech models, and then the agent basically you assign a number, and that agent gives it transfers to the nurse. So that's where the triaging comes. But what it does is that it saves a lot of time, and when you talk to that agent, it feels like a very natural conversation that you're having with another human being. And it will ask some bunch of questions. And then when it sees that, okay, the agent cannot answer any more questions of the patient, it will transfer it to the nurse. Similar to the prescription filling agent, it saves a bunch of time. It will answer the patient's questions about prescription. It will give you like, okay, what were the most recent prescriptions, or do you need a new prescription? It will ask questions like, okay, who's your primary care doctor, and so on. So these are some of the voice agents, and then also, that falls under the multimodality in the agents. And then, of course, the famous coding agents that we all know and use are Cursor, GitHub Copilot, Codex, and so on. There are like so many of them that I can't actually remember all the names anymore. So, yeah, this is how I feel like we have gone from experimental stage with AI agents to production. But I still believe that the human in the loop is still a component there, and we still need to figure out many nuances because what works in demos may not work in the production. And the from the big lesson that I have learned from my personal experience working at agent platform companies is that latency and consistency really matters. So for that, that is something that I know the companies are working towards, and something that we should even keep an eye out that, okay, this is how the agents in the production will work. So yeah, so this is all I had for this particular topic. Benoit, are we taking questions right now, or should I move on to my next topic and then hand it over to Rohan?
Yeah, let's wait for like till we're done with the entire cluster, and then we can go for questions. Thank you,
Okay,
Zonam.
perfect. All right. So the next topic, given that I was talking about human in the loop, it naturally transcends to the rise of vibe coding. Now, vibe coding is one, again, pretty cool topic. Everybody's vibe coding, when it first came out, I'm like, okay, what exactly is vibe coding? It took me a while to fully understand the lingo there, but now I do because, and I have a fun example to share about how I use vibe coding. Now, when we say or talk about how vibe coding is rising, it's basically coding where at least I come from the times when the first coding language I started learning was C and C++, then Java, and so on and so forth. And my God, learning how to code was a bit of a challenge for me personally. Now, all it is, it feels like it's I'm just talking in natural language with the IDE, for example, cursor. All I can do is that, hey, I want to build a website. These are my constraints, these are the guardrails, and this is my idea. Do something for me. That's literally how I talk to these coding agents. And uh, it's like you are steering and AI is executing. And that unit of work basically shifts from writing lines of codes to ideas plus feedback. And I sincerely love that fact. Now, what vibe coding unlocks? When I first started, I wanted to see like, okay, how much can it help and what is it doing for me? Basically, the prototyping of any application, whether I'm building an agent or building a website for my personal projects, the prototyping becomes seriously fast. And there is much less fatigue when it comes to like, that building that boilerplate kind of template. And I can more like focus more on system design. And this is true for developers as well, that they can focus more on system design. They can they can put their time and creativity there. They can build a prototype, and voila, you have a working prototype of whatever application that you are building. Now, so this is why like basically productivity goes up without really replacing developers. Now, one might ask, like, okay, can we do vibe coding and push it into production? I'll say no, please don't do that, because it may break. And we have seen many examples. I have recently heard people talk about certain models or certain coding agents, deleting the whole database and stuff like that. And it is scary. So this is why we want to keep humans in the loop because, of course, the context still lives with the humans. And AI is great at momentum, but I still think that it is terrible at judgment. And humans, at the end of the day, humans decide what good really looks like. And this is especially true when you are working in production code bases. It will create like, bunch of like, it will create your GitHub repo, it will write the README, everything. But it just like you need to have the review done from by humans, correct whatever you want, and make sure that the intent is aligned. Now, I want to quickly give an example of a website that I coded. And let me start sharing again. One second. So I'll take you to my cursor. So I have been building like a career advice platform. And this is my conversation. This is exactly how I have been vibe coding this particular application. From idea, from designing the whole application to the feedback, to the corrections, to creating a GitHub repo for my project. All I did was using Cursor. I honestly, so personally, I do not like front end coding and back end coding because my brain just stops working there. I do not know how Railway works. I do not know how Netlify works, but I was able to follow along and asked Cursor specific questions like, okay, what exactly are you building? Why did you choose this tool? And then when I would look into the code files, I would understand that, okay, this is what's happening. And um, um, the result of this vibe coding was this particular website. And believe me, I do not have any, like I said, I don't have any knowledge behind how to build this particular website all by myself. And all I had to do was just ask or talk to this chat with Cursor, and it basically created all these things that you see on my screen. So yeah, vibe coding is really cool, but highly, highly recommended that don't wipe code into production because that's gonna mess things up. So yeah, that's all I had for my talk, and I will hand it over to Rohan.
Hey everyone, how's it going? Um, what I think would be a great way to talk about the next section, which is going to focus on like context and memory, is to actually talk about what I think the world kind of looked like in 2024. And I know this might be a little bit of a controversial statement, but the way I think we operated with LLMs in 2024 is really thinking about, let's be very, very careful to include all the information and anything that we see, and context windows will just keep getting bigger and bigger, and LLMs will keep getting smarter and smarter, and we'll get better results. So we really focused on sort of the recall side of the problem. So what we found, though, is there was a lot of challenges and issues with that approach that I'm personally very guilty of myself, which is what I was doing more in 2024, is that it didn't necessarily work. And even though like context windows go to like 1 million tokens or 2 million tokens, and you can stuff in the entire book that you have, you still end up with a lot of issues. Like, for example, as you're adding that much context, even with perfect retrieval of information, so you know that the information that you're passing to a particular LLM, tasks tend to degrade. And that's because there's a lot of noise as well as signal in a particular document, and you're actually making the problem a lot more challenging for an LLM. Additionally, there are challenges where information is very easily found at the beginning and at the end, but things tend to get a little bit more missed in the middle. I kind of like to think about this as like when I'm reading through a paper and I start off and I completely understand what's going on, and then my eyes gloss over as I get to like page 2, and then I have to stop at some point and go back to the beginning and remind myself to reread. Going into the whole concept of like, once again, too much information means that, and really focusing on the recall side of the problem means that you're also possibly including a lot of noise, especially if you're not thinking about precision a lot of times. And the other part of it is when you have a large context, things often default to like local optimization. So because there's so much context and we have this focus on the beginning and focus on the end, there might be a lot of details and pieces in the middle that are really talking about how the entire system should work. So, but that ends up getting glossed over and missed. So you end up with actually a subpar product. And I think a good way to really think about this is like taking a particular example. And I think this example is pretty easy for us to understand, but I think it also really relates well to how an LLM might particularly approach a problem. So like you might ask a question like, hey, what was the best piece of writing advice I got from a college classmate? This might be like a test question or something that you see. And then you have a bit of a document and you have to find some information. So what you're doing here is you're essentially reading through this document and you're saying, well, a lot of this stuff isn't really relevant, but oh, this piece might be relevant. This piece might also be relevant. But the other piece of information here is that this is actually wrong. And there's a really good chance when you pass in all of this that the LLM actually focuses on this yellow section, the distractor, and actually gets the answer incorrect, just because there is some semantic similarity between this distractor piece and the question itself. So the way I think about context engineering is focusing a little bit more on the precision side of the problem, and how do we almost give the LLM a cheat sheet? Like, for example, if you, and once again, to sort of like humanize it or sort of make it more, to give an analogy, it's like if you had to ask a question of a book, if you had the whole book, that's definitely a much harder problem than if you highlighted sections in the book, which is still a harder problem than if you just ripped out all the irrelevant pages and just kept the 2 or 3 pages that you actually needed. So that's what I think about context engineering at sort of a high level. Now, before context engineering, we really had prompt engineering, and prompt engineering is still important. I'm not saying that we shouldn't still do that, but I think context engineering takes what we used to do in prompt engineering and really focus on a different scale. So for prompt engineering, the way I think about it is I think about it as we're leveraging the model's internal intelligence. It's much more static. We're trying to see the best way of how we can coax that particular information out of the particular model. Inherently, it's a stateless system, and it's a singular component that you're trying to optimize. And I just gave a couple of examples of how people typically think about optimizing prompts, which are chain of thoughts, persona adoptions, few-shot examples. Context engineering changes the problem fundamentally to think about how do we provide information to the model outside of its context. So fundamentally, this is dynamic, and it's essentially talking to multiple different systems, which I'll go through in a little bit. It's a bit more stateful because you want to preserve how the LLM is interacting with someone. And you also want to think about more of how do we remove distractors? How do we make sure that we're giving it relevant and useful information? So some questions that might be come to your mind is how do we just get better at this? So we don't obviously want to give the whole book. We want to figure out how to figure out what's the right relevant pieces of information. So some techniques are, for example, using like system to attention. So actually using another LLM or another system to take the particular context you're providing and stripping out anything that you find irrelevant. This still doesn't solve the distractor problem, but it at least reduces the amount of noise that an LLM has to filter through. Compaction is another technique that's very, very similar. So if you ever worked with like agentic coding tool, you'll see an option, for example, in Claude Code to compact your past history to only keep the most relevant information. That's also helping with managing how much you have in your context window and how you're actually improving it. There's other techniques such as like really thinking about context retrieval as like a problem that you can gamify with like a generator and a discriminator. You have something that's generating the particular context and a discriminator that's telling the generator where it's wrong. And you just keep improving and tweaking those solutions or that system, similar to like a GAN. You can look into things like better RAG techniques. So for example, like using a knowledge graph or having a better embedding system or a better embedding model. So you have vectors that are more relevant to your system, or maybe in your case, keyword search works better than embeddings. Or what we'll segue into is what I think is sort of like the sort of like shining example of improving context, which are memory systems. So in terms of memory systems, there's two aspects of this that I think that really focus on how do you improve things for context engineering. There is short-term memory, and then there's long-term memory. And the way I like to think of short-term memory is it's things that are more immediate in the conversation. It's part of your working session of you working with an agent or talking to an agent. So things such as like conversation memory, which are like what are the recent snippets or the recent things that you're talking to someone. The working memory, which are like tool outputs and intermediate calculations. So like what are things that we have from like calling some MCP server and getting back some details? How does that relate to the conversation we're having at the moment? And attention context, focusing on what is actually relevant to the agent at this particular time. Where do I want to call attention to in the conversation? But then to truly build like agentic systems that have really good context management and memory management, we also want to talk about other aspects of how do we think about this from a more longer term perspective. So for example, like factual memory, so things that the agent might know about the particular domain or the user that it's derived from prior conversations. Episodic memory, so thinking about things that has happened in the last conversation or the two conversations before that. I know those kind of feel a little bit similar, but the way I sort of distill or separate those two is thinking about it in the lens that here is something that I've been able to distill as a fact about the user and from a factual memory perspective. And the episodic memory is something that I think about is here's something that might have occurred in a prior conversation. It might eventually become factual memory over time, but usually factual memory is a much more declarative way of speaking or a declarative statement that you've given to the LLM. And last but not least, we have semantic memory. So really thinking about the relationships between different concepts that have been introduced. But once again, to kind of anchor this, I think it makes sense to like think about this in the lens of like what might happen if you go to like a local coffee shop and order a drink. So when you're ordering a drink, you might say like, hey, I want a latte. And the barista might say something like, well, do you want it hot or cold? And you say hot. And the resulting part of that conversation means that the barista is going to make you a hot latte. It's not that you told them explicitly up front that you wanted a hot latte. It's that you're keeping track of the particular elements in the conversation so that you know how to chain those together into like what the actual customer wants. Working memory might be say like, hey, the latte costs like some crazy amount because I live in New York City, but let's say you add a bagel to that order. And so like adding up the price of those particular pieces and putting those together to get some sort of value of like how much the total order is. Attention context is saying like, hey, I'm in a rush, so I'll just take whatever you have that's readily available. So kind of bypassing the particular order, understanding that the rush is a key element. So what is the fastest thing that I can make? When we talk about long-term memory, it's something like where if you go to a local coffee shop and you're a regular, where someone kind of just knows your particular order, because that's the fact about you, is that your typical order is you always get this particular drink. But episodic memory, the way I would contrast that is knowing about what you ordered last time or some element of a conversation you had in a prior visit to the shop. And lastly, semantic memory might be on top of knowing that usual order. It might know that, hey, when it's cold outside, I'm going to relate cold to this person wants a hot drink. But when it's hot, when it's summer, I want to relate that heat to someone might want a cold drink. So knowing those aspects of it and knowing the relations of all those pieces. Focusing on some notable papers that I think really helped me clarify a lot of my understanding of this and helped me from a professional context is I listed a few out here, but one I think is a survey paper that really covers the breadth of context engineering. One is like really talking about how a lot of context gets lost in the middle and context rot about how just increasing your input tokens can be problematic. And last but not least, for memory systems, one of the memory systems I've had experience with is Mem0, and I think they do a really good job of working with how they represent and curate memory. I think their definitions of how they define how memory works is also very interesting. I'll pass it off to Sophia.
Awesome, thank you. Let me share my screen first. Window. All right. Cool. Can you see the Miro presentation, everyone?
Yep.
All right, cool. So building on that idea of context management, MCP, oh yeah, and I'm using a very funny image. I was trying to make a cool one like Sonim's, but didn't really work out as well. So just building on the idea of context, MCP takes it a step further by providing kind of a structured way for models to access, organize, and reason over context reliably. Just to kind of ground us in what we're talking about, we're going to chat about what MCP is, how it interacts with LLMs, and some examples of some issues with it and ways to implement a server for your own application. So as I was researching this, or just looking up what people are talking about, I kept seeing MCP described as like the USB-C of AI or the REST API of LLM apps, and all of those work fine. Whatever makes the most sense to you, you should just go with it. It's an open protocol that lets AI models securely connect to tools, data sources, and applications. And open protocol meaning that no vendor owns it. All the implementations work the same way because they follow the same rules. So instead of every agentic framework inventing its own tool calling wrapper, MCP provides one standardized way for any AI system to kind of list what tools are available, send structured requests, and received reliable and typed responses. And just under the hood, it uses a communication format called JSON RPC, and that it basically any tool that can speak MCP can read and write in JSON messages, so it's pretty language agnostic. And let's see, next slide. So what's here? So under the hood, MCP is built on a client-server relationship. There's three components to it. There's the host, which is any AI application. So Claude Desktop, Cursor, Copilot provides an environment. The host loads the config file, manages conversation and state, and then runs the MCP clients themselves. And the clients are hosted inside, or are inside the host, I should say, and handles the communication, opening the connection, sending requests, receiving responses, kind of the gateway to the server. And then the server is kind of where all the capabilities are. So the server exposes structured features such as tools, so like the types of actions the LLM can invoke, So maybe if you have like you see this example everywhere, like a weather API, an action could be get weather, or you could also create an action for get Jira ticket. There's also resources that the MCP servers expose, which is just pulling data or content that an LLM can request. And then for prompts, just like reusable templates that the LLM can call. And so they're all sandboxed applications that can define what they do, and they return data. Let's see, like the connection. Oh yeah, okay. So the images on the right, I just wanted to kind of like highlight like the exchange that takes place between the client and the server. So this client asks the server like, "What can you do for me?" And the server responds with the structured list of things like the tools, resources, and prompts. And then the client can acknowledge, and then it proceeds with like the action. So for like the weather API, again, like it might have like a get weather tool, forecast prompt, maybe a set of resource endpoints for collecting like historical temperatures. I don't know. So the LLM will know after this exchange what exactly the server can support. So just comparing to like a traditional API where you must like hard code all of the request formats, with MCP, servers like self-describe what their capabilities are. And if you like want to add another tool or another prompt, anytime the clients access it, it will see the latest definitions of it. So it's just very convenient, you gotta say. And then one other final piece to kind of go over quickly is just that LLMs do not make the API calls directly. We're talking about agents, right? So the LLMs here, what they're explicitly doing is outputting a structured tool call. And one of those, and I'm sure we've all seen those JSON structured responses, but it can be in any format, but we're saying that MCP is the structure that you should use. And it just basically describes what it wants done. And so then the agent, the piece of software running this LLM flow steps in. It's like either your Python code, it's LangChain, it's the Claude Desktop, Copilot, etc. There's a loop that happens, and then it reads, basically the agent will read the LLM output, sees that it's a JSON, executes it against MCP server, and then gets the result back and adds it to the LLM context. So that loop continues until an answer happens or whatever endpoint you set up for your flow. And so just going on to kind of
Can you make your screen a little larger? People are saying they can't see it.
Oh no. Okay, let's see. Yeah, right. All right, good. And I guess, we'll be sharing the links for this afterwards, right? So, okay. So thanks for letting me know. So I'll just go to Anthropic's page just to show this one. But let's see, what is the model context protocol? Okay, so why is MCP the standard now in 2025 and 2026 moving forward? As I kind of mentioned before, there's already agent frameworks out there. Everyone had their own wrappers and for tool calls. So MCP, again, just solved that by offering one universal interface. And you can see, like a lot of industry adoption. Recently, part of this announcement and this blog post is that MCP is being donated to the Linux Foundation. So it's going to now have community neutral, vendor neutral evolution. And then, of course, like over time, there's been more and more community and official servers that have been released. And again, there's also MCP SDKs in Python and like TypeScript, and I think they also said Go and Rust. So there's just a lot of different, there's a huge momentum here is what is going on. So going back to the slides. So just some examples, and I'll, again, like these are all different links that when you get the Miro board, you can kind of click through as you like. But So I looked at a lot of different MCP Reddit threads and tried to get a good understanding of what servers people are actually using. And again, if you have any that you are using, you should put them in the chat, or you can also like highlight it during the Q&A time. I'm very curious to see what people are using for their own application development. But so there's, again, a lot of official and community-based servers. And so these few on the right-hand side are kind of what's used for demonstrating features of MCP. There's like sequential thinking, oops, click the whole block, that basically is a chain of thought prompt with additional features for planning, reasoning, and you can adjust your plan. It like branches out. It's like an interesting way to basically create chain of thought prompting in your LLM context or LLM state. And then another one I heard of is called Context 7. And so that if you're working in Copilot and you can't use, well, I guess if you have access to web search, I currently do not in my financial lockdown environment, but you can use Context 7 to, let's see, like if you're like working in a library and it constantly is getting updated, something like LangChain, where like there's new releases pretty often, Context 7 will actually pull up the latest docs into the context and like allow you to actually debug using the latest, if you're using the latest library. So that one seems pretty useful. So moving on. So what still needs work with MCP? All this, it sounds really great. There's a lot of momentum, but there's still some important gaps in the ecosystem that everyone's trying to work to solve right now. So there's inherent security risks with giving AI agents access to real systems. It's a pretty high stakes situation. So once an agent can take action, it becomes an active participant. So MCP was not designed for security. It was kind of it's like agnostic to it. It handles the plumbing of tool calling. So again, like listing tools, calling tools, returning results. But MCP doesn't really define who is allowed to call a tool and like what are they allowed to do and how those actions should be audited. So that means all that must be handled externally. And same deal with like unauthorized access concerns and monitoring and oversight challenges. And there's like vulnerabilities to prompt injection as well. So there's, again, like people are coming up with solutions, and I have papers at the back of this that kind of highlight like what the overall like security frameworks are and what some solutions are being built in to like make that easier. Because if you use a community server, MCP server, you really have to do that background check on yourself. You can't like necessarily trust everything that is being like put out there because it's still early days in some ways. And so, just to get to kind of the wrap up, there's a few papers that stood out. There's, of course, like this first one, which is like MCP landscape, security, threats, and future directions. So it's kind of an overview of all the architecture, the risks, and the life cycle of MCP servers. And then there's the second one, which we actually talked about in the August or September reading group, which was basically a benchmark, a continuous evaluation benchmark that stress tests agents across 101 real-world dynamic tasks and expose some weaknesses within some of the reasoning models that they used. And so it was a good example of continuous evaluation, which I'm going to talk about next. And in the paper, they use an LLM as a judge that judges the final output based off of the efficiency of the tool calls, like did it follow the most efficient path, as well as whether or not it sufficiently completed the task at hand. And it showed, I think, like all reasoning models have like an 80% completion rate or like successful completion rate of a task. So it like alluded to the fact that maybe there's more like development in LLMs right now where they need to be able to support better tool calling or more efficient tool calling. And so this last paper is called Securing AI Agent Execution, and it's kind of the first proposal for a security framework for MCP servers. Cool. And so, yeah, these papers all kind of were helpful for pushing like the open source community to like figure out MCP implementations. And so I guess I can just end on how you can try MCP. You can actually just use it on Claude Desktop or Copilot. You just have to add servers in the developer mode in the config file. There's a lot of videos on how to do that. And then you can also use the official like SDKs for building a tool and making it available. I think it's pretty easy. You can use like standalone like Docker containers as well. So yeah, so that's a wrap for MCP for this year. And so I can actually go on to the next topic. I see lots of questions coming in. Okay, yeah, so still sharing my screen. So let's go to the next beautiful artwork for this next topic, which is continuous eval framework superseded one-time benchmark validation. So basically, to set the context here, it's LLMs now are powering a lot of different types of processes. So they like power chatbots. They're part of Copilot. They're used in search now and lots of different decision tools. So I'm sure like it. I don't know if you have your managers that like talk to you about like, oh, what's the deal with this model? What's the deal with this model? And it's like, it would be a full-time job to like review all of the latest LLM releases as they're coming out and identifying the strengths and weaknesses of just all the different implementations. But just to say that LLMs, like their behaviors can change and they seem to change constantly. So we need an evaluation framework that keeps up with that. And so let's start with like the basics, the good old days. In the good old days of transformers, early transformers, we relied on some handful of well-known benchmarks. So I've listed some of the classics there. And so, for instance, like you can see on this squad, this is actually a leaderboard for the squad benchmark, and you can see like all the models are steadily pushing towards the exact match accuracy higher and higher. So it's like pretty simple. It's like almost like you look at that and say like we have solved NLP. But you know, there were actually problems with this. So as soon as models more models got on the scene, like, you know, models can start to memorize benchmarks, especially if they know what benchmarks are going to be tested on. And so as soon as like a field discovered a new data set, it spreads everywhere and models can like study the test. And then these benchmarks get outdated pretty quickly. So a data set built even like a few years ago probably can't tell you about how a model performs on tasks that uses knowledge from 2024, 2025. And so once models hit like human level evaluation, the benchmark kind of stops telling you anything meaningful. So they're good for early progress, but it seems like they're not keeping up with pace and complexity of modern LLMs. So they're not like fixed models. So every update has the potential to shift how the model behaves. So without reliable evals, you're like shipping this LLM into the void essentially. So on top of that, models work in unpredictable dynamic environments. So, millions of people ask them lots of unique questions in different languages, different contexts and format. And so there's no static test that can represent that. And so new behaviors emerge all the time. I'm sure maybe some of you heard of like semantic leakage in GPT-4o. I think this was like from a few weeks ago, where models leak irrelevant information from the prompt into the output in unexpected ways. Like he likes yellow. He works as a fill-in-the-blank school bus driver. So it's like, how do you debug your prompt sufficiently against all of the different biases that come out of the LLMs? And if there's more biases being discovered, like how do you keep up with those? And so let me zoom out. There's also I'm just like pulling up recent ones, but there's also subliminal learning where let me zoom in, where models can unintentionally learn patterns from signals that were meant to be hidden. And so if the parent model, let me see, such as, so they were meant to be hidden or irrelevant. And so then it causes them to be picked up later in the child model that they weren't allowed to access. So again, like these papers are here in case you want to check it out more. But so let's see, did I cover everything here? So yeah, lots of that. And then another piece is actually like the the way that we're testing models are in such dynamic, unique environments that it might be difficult to find human labelers for every single instance where you'd want to test. So this is where potentially using LM generated test sets and using LM as judges can be helpful here in terms of scaling these like testing evaluation frameworks. Okay, and so some of the key drivers for this continuous evaluation is there's been a big ecosystem built out of it over the last couple of years. There's Stanford's Helm, there's OpenAI evals, which has like community contributed tests. There's Hugging Face, as we all know them, and then there's also Chatbot Arena that like allows users to compare head-to-head different models, which allows like for human feedback at scale, which is great. And so kind of wrapping up here, let's see, as models have gotten more capable and more unpredictable, so we've shifted towards continuous eval, and this looks, and this style looks pretty different from the old, single one-time static benchmark. So it means testing across multiple dimensions. So not just accuracy, looking at reasoning, safety, bias, multimodal skills, what matters for the actual job as well. So it makes it more realistic, but it also is like a more complex task at hand as a developer. You can also update how you do scoring, and so you can do rules-based checks in addition to LM as judge scoring, in addition to human in the loop agreements. So rules-based systems can handle easy things, LM judges can scale evaluation quickly, and humans can step in for like the nuanced edge cases where more like subjective judgment is needed. So there's also more task-oriented evaluation, which I kind of already mentioned. So instead of trying to optimize your LM for just this like blanket statement of improving productivity, maybe you are more specific so like whether that's like summarizing like legal documents, writing SQL, and answering medical questions, like how do you evaluate how well it's doing those specific tasks? So what it's actually meant to work on. So not like abstract proxies or whatever. So continuous evaluation has become the standard, not because it's like a flawless new system, but it seems to be the only approach that's flexible enough to handle the constant change of modern LLMs. So I think that's it for me. And so I guess we're switching to questions now, right?
Correct. Let me take it from here. And correct me, even though we have 5 minutes for questions.
No, not really. Let's just take the top two questions. Honestly, we're running slightly behind on time. But
Right.
if we
I
have
was going
some
to ask.
time after all the clusters are over, we can come back to questions. By the way, Arthur, there's a bunch of background noise from your end as well. Letting you know.
Okay, it's not for. Can you shut down everybody except me because it's not me.
Done. All
Thank
right.
you. Okay, we got it. Sounds like it's gone. All right. So Nahil, you want to ask your question?
Sure, yeah. When Rohan, you were chatting about, like improve context engineering versus prompt engineering, a question came to mind is there are all these different techniques that we can use to do context engineering. Is it like the same strategy to evaluate like prompts against each other of how you would do context engineering, or is there a better way to say, like this works better in practice for these type of tasks, so to speak, like use system 2 versus use compaction versus this for these type of tasks?
Yeah, I think it really depends. Like a lot of it's going to be very contingent on your particular data set and like what you're actually trying to do. So I don't think there's a one size fits all. But if you really want to talk about evaluations, then I think there's two ways to really take it. There's like the integration test scale where you treat the entire system from query, you treat like how you're pulling in information and your agent's response as like a black box, and you're sort of validating like, is your agent's response still looking okay? And I think that's kind of how you approach it from a prompt engineering perspective. Like the prompt is a part of the like how you're calling the particular LLM. What context engineering allows you to do is think about it more in the scale of like specific like sorry, not integration, end-to-end test. But if you want to really think about it as a series of components, let's say you have like some memory system which you're pulling in particular information. Let's say you have a system which is doing compaction. You can do things like context recall and context precision on this particular subcomponents. So you can essentially say like, hey, I'm getting a really good recall score here, but I'm getting really bad precision. So depends on your system. Once again, maybe that's okay. But essentially you can evaluate those subcomponents independently and then use that. You can still do your full blown end-to-end test, but you can do your more subcomponent based tests as well and evaluations.
Cool. Yeah, I think that makes sense.
Okay. Next question, because we're short on time. Vignesh, would you like to ask your question? You're on mute potentially, Vignesh. Okay. All right, I'll read it, Vignesh. I see your note. So Vignesh asks, so are MCP servers often doing the context engineering for any context made available through them, or does context engineering still fall on the user's side on top of what they do to optimize further to your use case? I don't know who that's directed to. It sounds like it's Rohan, but I'm not sure. Oh, no, I'm sorry. That's Sophia. It's MCP.
Yeah, so like where could you restate the question? It had a couple different pieces to it. So it was, what was the first question?
Hold on.
Yeah.
So our MCP servers often doing the context engineering for any context made available through them, or does context engineering still fall on the user side?
Yeah, it seems like it falls on the user side. Because the tool just accesses like potentially like, I guess it does manage context in some ways if you're like using the MCP to extract or pull in data that's using an additional loop of reasoning. But it kind of depends on how you've set up the flow. It sounds like how like context engineering is used.
My experience is how you architect it. You can
Yeah.
architect it either way.
Yeah.
All right. I've been told 2 questions only. So we're going to move on to session 2, which is multi-agent orchestration and model cognition. This is going to be handled by Nihil and Valdemar. So I will turn it over to Nihil and Valdemar. I don't know which one of you is speaking first, but go ahead.
Yeah, I think Valdemar is not here, but Lucas is joining us, and it's his first time. So welcome, Lucas. Take it away.
Yeah, pleasure to be here. I will be starting about I can start with the multi-agent part. Let me share my screen. Yep. Okay, so yeah, I prepare a little presentation here about the multi-agent orchestration and talking about a little bit about research, also some production use cases that I prepare. So first, we talk here in the session about agents and also MCP. I think all this relates to this broad concept, which is the multi-agent systems. So if we think that in some analogy with kitchen, we can think that we have an orchestrator, which is the head chef, which makes planning, the delegate tasks, and we have also some sub agents, which are specialized on doing certain specific things. Like for example, if you think in a kitchen, like for pastries or for like seafood or for entries or desserts and things like that. So if we think in sub agents in general, you can have, for example, a sub agent which is specialized in coding or in testing or in writing documentation. We can think about many different types of use case. And the main idea is that this orchestrator role it is like a central brain that delegates the task to this worker. So it needs to have certain type of um, responsibilities, like for example, planning or understanding what sub-agents should be used for each specific tasks. And of course, one of the main parts is how you communicate. So if you start with this more complex architecture, you need to have some type of communication protocols. So one of the ways, like, is, for example, if the orchestrator wants to call a sub agent, it can generate like a JSON request, and then your system can read this and call the sub agent. Well, that's done also for like popular package like LangChain, LangGraph. They all for using that you can implement this type of systems as well. And the third part, which is really important, is that you have a memory which is shared between the sub agents, the orchestrator. Also, that can be defined depending on your application. But in the end of the day, you need to have some type of collective memory when you are building this type of multi-agent system. So with this said,
Can you hold
I
on
want
one
to.
sec? I need you to put your thing back on mute. I'm about to mute everybody and then unmute yourself. Okay?
Okay.
Okay. Now you should be able to unmute yourself.
You know?
There we
Good.
go. Thank you.
Okay. Okay. Good. So continue on this, and here I will go back. So I prepare. So defining the multi-agent system in general, I would like to talk about a research paper that I read recently, which implements like a research playground of this with a multi-agent system, which is really interesting. So in this paper, they are building this multi-agent system for playing Minecraft, and it's all based on LLMs. And to test some type of new features that they are proposing on the paper. So so normally when you have a standard agents, they work like in serial. So you think, and then you act, and then you think again, right? And the interesting part of this research paper is that they try to parallelize the planning and acting part of this multi-agent architecture. So as I told, like normally when you have this orchestrator, you need to have a planning part, right? Which calculates like what are your goals, what are your long-term goals, how you plan to solve this X problem, and also have the acting task, the acting thread, which are mainly the sub-agents which interact and perform tasks, right? If you think in this broad sense, you can separate like that, right? And in this paper, they try to get this system and make it a little more complex by allowing the planner to stop the actor if something changed, right? And in this scenario here, it's a made up scenario because this multi-agent is implemented for playing a specific game, which is like Minecraft in this case. And you can see here that all these parts that I presented, like they have a centralized memory, which contains the records that were observed, the chat logs, the actions that were taken. You have the planning and the action part here in the middle. And you have also the resources that you can get. Here they are like resources that you need to get so you can advance in the game. And in this scenario, it's really dynamic because the environment is changing every time. So what you're observing, your observations, they are changing and you need to adapt with them. So in all this context, it makes sense that, for example, orchestrators can pause or can interrupt some other agents. Uh, so if you can finish the task in this.
Lucas, sorry to interrupt, man. I think your audio quality is dropping drastically. I'm not sure what it is. There's like a bunch of background noise, and we can't really hear you right.
Let me see one thing. I think my.
Yeah, we can barely hear you.
Can you hear me again?
Yes.
Um,
better. Yeah.
Okay. Yeah, I think my battery is dropping. It was in the. Let's see if it's better now. Is it better?
Yes.
Okay. So continue here. Um, in all this scenario, well, we can see that it's like a complex scenario that to deal with, and this is where the research, uh, like the research paper try to act, right? And and then if we go to the production reality, if you step in the production reality, I think one of the main use cases that we can see now is on the coding agents part. Uh, and I've been using a lot of coding agents in my job as well. And one of the coding agents that uses this multi-agent architecture more is the Cloud Code one. And they already deployed this. And the way that it works is that you can create sub agents and you can assign specific tasks for these sub agents. And for example, you can create a sub agent that just analyze logs. And you create this, and the loop which goes is like you have the main agent, which is the cloud code. And if it identifies that there is a task that is suited for this sub agent, if you call the sub agent with less context, so you can just focus on solving this specific task, right? And this is how they are implementing, for example, in Cloud Code. And in this case, the sub agent is really specific for like a task, right? And the environment that is the sub agent C is also really restricted because they are more interested in making the sub agent works well for this specialized task instead of trying to create a more general sub agent. See? And here we can see that this is from directly the Cloud Code page that they say what the main benefits are of creating these sub-agents. So for example, here we have the context preservation, which the sub-agents operates on its own context. The sub-agents also have a specialized expertise. You can reuse the sub-agents or for other tasks. And you have also permissions that are flexible from these sub-agents that can maybe access tools or limit it to just some capabilities. So with all that said, I want just to trace here. I presented basically one research implementation and also the production one. And there are there are similarities, then there are differences as well. So in the research part, the objective is made up. It's like you are trying to implement a system that is used only for a game, and you are basically creating using the complexity of the game to create a better system. And the objective in the end is just surviving in this made up world, in the game world. Whereas in the production case, we are really concerned with being reliable. So the sub agents, in this case, the multi agent architecture needs to be really reliable for everyone, for the developers that are using. Also, the environment is a big difference. And the strategy that was implemented in one is also much more complex than in the production. The research strategy is much more complex than the production one. And also really important, the constraints. When you are talking about research papers in general and research papers implementing this multi-agent system, you are constrained by the computational power, where in production you are really concerned with how many tokens and the latency that everything is implemented. So just this parallel, this just trace how can we go from the research implementation of these complex systems to actually a real world one. And I think bridging this gap is a really important thing to understand and to discuss going to the future as well. Yeah, that's it for my part. I think Miho?
Cool. Yeah, I can take over. Let's see. Let's share screen. Once I share screen, I won't be able to see the cameras. So yeah, like if you guys want to interrupt, feel free to do so. I want to make sure that the content is legible, so I'll just zoom in, zoom out. Uh, since the beginning, we've been hearing about different agents. They're able to increase context. We need to get the right context. Then they're doing tool calling. Now we're building multi agents. And behind the scenes, what's happening is like the labs are working on increasing the quality and the capability of these agents. And I wanted to talk about how where that is, how people are doing it, and how that changes for engineers and ML engineers specifically, because the world is getting to a point where most likely we all will be taking some part in not just being at the application layer where we're just writing some prompts and connecting systems and architecting them together, but maybe we have specialized tasks and enough data that we have to train our own. For example, like Sophia was talking about this example, which I see in industry right now very commonly, where you have a constrained environment, like you don't have access to all the tools that would have made the agent actually work, but you have the data to help you actually build the agent yourself, which can inherently do the reasoning in that part of the context. So earlier this year, I think in January, that was the first reading group we did, and it's kind of feeling full circle where DeepSeek R1 came out, and DeepSeek R1 was like, hey, I can do what OpenAI has been doing for so long in much cheaper time and resources. And everyone was like, oh my God, what did they do? Like, OpenAI is not valuable anymore. And so let's kind of understand what they did and how that'll change us fine tuning. Like, what does RL mean? Or what does human preference, human feedback mean, stuff like that. So I just prepared some slides around that stuff. This is where, let's zoom in. So this is a blog post by Chip Hewen, which kind of talks about how ChatGPT was built. And this is a good place to kind of anchor and understand what has been happening behind the scenes of all the application layer stuff that we've been doing. So reinforcement learning was actually pretty hard and not related to NLP. So people who are becoming experts in NLP like 4 or 5 years ago did not know anything about RL, reinforcement learning. And so ChatGPT was like the first production system. It kind of brought them together and showed, hey, there is value of bringing RL into the NLP world. But the techniques that were used for RL were there for a long time. And so this is the process that actually was used to build ChatGPT at a very like theoretical level. And there are a lot of steps. Of course, it was trained on internet level data. And then we got this model, which we call the pre-trained model. It's very possible if you guys have been like self-learning on doing transformers or LLMs, etc., you might have seen different parts of this or maybe even the whole thing. But because we have a broad audience, I wanted to make sure that we're kind of anchored into the concepts here. So on the internet stage data, which is like raw data, just take a lot of data and say, hey, can you predict the next word? Can you predict the next word? And that thing is called pre-trained LLM. And as Chip Hewen was saying, this is more like an untamed monster. You don't really know what's going to come out. And you can't put that out in front of the world, right? Like you will most likely blow past ethics. It might not be sensical output, so you cannot actually use it either. But it has understanding of the repeated patterns that we know as human knowledge captured in internet data. So we know that. We're just not able to kind of understand it. So then what happened was they took lots of human labelers, and that was actually not even like taking human labelers. They just scraped data from high quality data sources like Stack Overflow, which has, hey, this is my question, this is the answer, Quora and stuff like that. So they got a lot of high quality data, which is not at the scale of internet data. Internet data is trillions of tokens. This is more, as it's written here, right? Like 10K, 100K type of tokens, or words, so to speak. And so the data set is much smaller, but it's much higher quality. And they train it again on that. So that's called supervised fine tuning. You're supervising, given this input, this is the output you should think about. And training the model to actually get better at doing that. That is what the supervised fine tuning model is, usually referred to as SFT models. And then even then they were like, okay, this is still not good enough because it is uh, it is okay in terms of giving coherent answers or somewhat coherent answers, but they're still not like ethical or they're not good enough. And then came, hey, okay, can humans actually understand the different pieces of what is good and what is bad for a given answer and do another round of feedback, which is human preference, human feedback. And then they are like, okay, this is going to stay in the bounds of what human thinks is the correct answer. And that is RLHF. And in this diagram, you will see like RLHF actually is almost the same size of the box in terms of complexity as an engineer to look at versus the previous parts. They use a technique called PPO. PPO RLHF because they're using it on human, they're doing RL on human feedback. And the whole part of PPO is that it's a reward model. And so you need to have a reward model which kind of takes your comparison data, this is good, this is bad, and then classifies the output of the model and creates like a loop of, hey, get good reward here, you get bad reward here. I mean, there are more technical mathematical understanding, but I'm thinking more from like architecting the system and the flow of data and kind of what are the different pieces you need to actually make it work. Or at least they made it work with ChatGPT. You'll see further down the line that it's kind of simpler now to do that. There are lots of libraries which will help us do that. And that gave rise to ChatGPT. So there were these three different techniques that were used. One was just pre-training, which most of us don't have the budget ever to do. Then there is supervised fine-tuning, which we can do if we have enough data. And then there is RLHF, which has seen a lot of different um, research and like innovation there. And it's still early days. Like there's still more ways that might come out next year, which I'm personally excited about. Um, so in terms of like how is it relevant for us, there are a lot more boxes here we can put for different types of trainings. Like this is called post training, where you have a model and you're training it to do something specifically better. And that gives rise to extended reasoning and kind of long context, like, hey, do a thinking block, do a solution block, and all of those things. And how can you actually make your LLM do that specifically or in your context or your task? There are different techniques for that. So let's look at some of them. So the top row is actually SFT, which is like you have input output pairs and you're just helping the LLM get better at, given an input, how will you get a good output. And then this bottom row, and GRPO is what DeepSeek R1 came out with, is more RL. And here what is happening is, this is the thing that I just talked about. And then GRPO is basically group relative preference optimization, where what they are doing is they're doing something slightly different than PPO. So let's go one by one. So SFT is basically you have a base model, you're retraining it with high quality data, and it's usually examples like, given this input, this is the output, and you just curate and make sure that the input output pairs are higher quality than your base data that you use the base model training on, that you train the base model on, and so you'll get a slightly higher quality data. It is not that effective and you need a lot of data. Then there came a technique called DPO, which is direct preference optimization. Here, what you're doing is kind of what Chat Arena does. You get two responses. ChatGPT also does this, where you have two responses and they say, hey, do you prefer this or do you prefer this? And you're getting direct human preference. And then you're using those data sets to make the LLM choose a given option of the multiple answers it can produce. So that is called DPO. And then KTO is not so popular yet. Maybe it will become popular, but it is very similar to DPO, where you don't have a detailed output, but you have, hey, is this, or you don't have a detailed comparison between multiple options. You just have one output and you have a feedback symbol of, hey, this is good or this is bad. And then you're training your model to only behave towards the good answers and not the bad answers. So a little bit like RL, but it's not using RL. It's just like simple pairs of input, output, and then was it good or was it bad? So those are SFT techniques. And then we have RL techniques. The RL technique, the standard, like the long-term way of doing this has been PPO, where you basically have a reward model, and then given an input, you're like, hey, is this, will you get a good reward for it? Will you get a bad reward for it? And based on that, you will improve the model itself. but you need two models. So it's memory intensive. You need a lot of huge infrastructure to actually make it work. GRPO is different. What GRPO is doing is it's saying, I don't need the reward model, but then how do you actually figure out reward? What you actually end up doing is you create heuristic based rewards. So that's what DeepSeek R1 did. What they said was, we will make our model. They were using V3 as the base model, and then they were saying, hey, I'll give it reasoning and I'll make it work really well on the quality of coding and mathematical tasks. And based on that, I'll just inherently see an emergence in better quality of intelligence or the output. And so what they did was they took an input and then they create a bunch of different outputs. So that's the group of potential outputs for a given input. And then I have a heuristic, which is giving reward of saying, hey, relatively, these few answers are better than these few answers. So next time when you try a task like this, try to get towards a better group type of output rather than the bad ones. And slowly, this builds up towards a better model. And I think the value here is that you don't need to train another model which does reward, and so it's much easier to get started. And I'm seeing more and more in practice that GRPO is becoming the standard when you're saying, hey, I want to do RL. And then if you just want to do supervised fine tuning, DPO is still kind of, SFTP is there, people are doing LoRa's, but it's not very common to do SFT anymore. It's mostly DPO, and then for RL is GRPO. Okay, so what does it actually look like in practice? There are a bunch of different libraries. I have played around with SkyRL, and so I can talk about this, but I think the concepts overall align on all the different libraries have the same RL concepts. So from an engineering architecture perspective, how do you train a post-trainer model with GRPO or PPO? So you have a controller which kind of moves the data and makes the model work between a trainer and a generator. And then a trainer is going to have some kind of a training loop. Most of the people will use FSDP, which is like fully sharded data parallel. It's just a way to use lots of different GPUs and like load lots of data on it so that you can actually train a big model. Otherwise, you're stuck with smaller models. Then you can't encode so much knowledge, so to speak. And then generator is taking that same model and doing inference on it, where like, hey, given this input, can you give me an output? There is no updating of weights, which is what actually changes or improves the model itself. And this inference engine works closely with an environment. And for most engineers, the thing we will be working on in 2026 is actually going to be mostly environments first, because you have many inference providers already. Training is mostly standardized. I mean, I think that's more researchy, the training block, and most people don't change training. But the common thing to change is one, of course, the kind of prompt, which is part of the input, and the environment, which is the task that you're doing. And there are different paradigms and APIs coming out of how you write your tasks. And of course, they are reusable. Like if you're building a SWE agent, probably file editing tool is like the most common tool. Why everyone needs to implement their own file editing tool. And so that's where the world is going. Just wanted to flash that for you all, that like if the world gets to a point where, or if in your work, you're like, hey, I want to do a RL based fine tuning, it is not very hard anymore. It's getting easier and easier. All you need is infrastructure and then learn one of these libraries. I can show you an example of what SkyRL training will potentially look like. So they wrote a paper about how to do text to SQL with RL. And inside that loop of the generator, what is actually happening is you get a question and then the environment is the database. So here what's happening is you get a question, the agent thinks of, hey, what should be my prompt, like response to the prompt? It generates a SQL query. In the environment, it runs the SQL query. In the environment, there is another function which knows, hey, how do I actually get the right response? And can I do a code-based matching of this output is exactly the same as this output? Okay, then I can calculate some reward based on the matching of the output, and then you give the reward back, and then you keep looping through this, and that's your training loop. These are some examples of how you can even make it do multi-turn. This is how you develop extended thinking. So you get the model to do a lot of different iterations of thinking, SQL, observation, and then you kind of using GRPO say, hey, these turn 1, turn 2 were great. 3, 4, 5 were bad. Don't look at that. And then eventually you get better and better turns. And yeah, that's kind of it. And all you needed to do was figure out how to set up an environment with SQLite, have some data set to, because you need to know what the correct output for an input prompt is. And so there are data sets already which talk about, you can create a synthetic data set in SQLite, and then there's an English prompt to ask a question, and then a SQL output as well. And so you can use that to train the model to do a better job. And they used Quen 2.5, but you can use any model that you want. And this is what one example of the data set looks like. I think it's fairly standard and kind of makes a lot of sense. This is the name of the database because the data set had many different databases. This is the question, and then this is the correct answer. This is like, if the output of this SQL matches whatever the model is giving from the question, then that is the then you get a better reward, versus if not. And then this is just some syntactics on like what synthetic data to use to create your SQLite database.
Nihil, since you're at your last slide, I'm going to stop us because I want to make sure our last speakers have time, unless you have something major more to discuss, because I see your last slide is references.
Yeah, that's it.
Are we okay? Okay, good. I'm going to skip, if you don't mind, Benoit, because of time and the quality of what's coming from these speakers. I'm sitting here just in awe of you guys and what I'm learning. So I'd like to just jump to Adam and Anna, let them talk, and then we'll have questions at the end. Are you guys okay with that?
Yeah, let's go for it.
Okay. Adam, Anna, you're up.
All right, Adam, do you want to go first, or I can cover first and then try to leave enough time for you?
Yeah. Go ahead, please.
All right. Let me try to share my screen. All right. Are you guys able to see this?
Yep.
Okay, I'm reusing my slides from a previous conference, so please disregard the logos. My design team put this together, and it looks much nicer than what I have. So just gonna reuse it. All right, I'll get right into it. So every day you see a new recommender, chatbot, summarizer shipped. It's an exciting time in tech, but a troubling pattern is that your model performs well on technical benchmarks, but there's no guarantee that they will accrue to a business's goal. Without carefully testing and validating, these once exciting new features often fall flat. Users bounce, trust erodes, and support tickets spike. This is no coincidence. This is the gap between offline model validation and real-world product success. I think in the question and answer sheet, Vignesh has asked about whether we will be comparing online versus offline. This presentation will cover that. So the AI evaluation crisis, the MIT Technology Review, quote, human preference testing has also emerged as an alternative to benchmarks. AI researchers are beginning to realize and admit that the status quo of AI testing cannot continue. The problem here is that many AI developers and leaders fail to understand that AI features are about more than just the model itself. In the real world, it's about the UX, context, and user goals surrounding them. So I'll introduce the ways product leaders are addressing the AI evaluation crisis in practical steps. The core problem here is that benchmarks don't measure reality. The evidence is overwhelming. To list just a few, Meta's Galactica scored super well internally, but was pulled back within 3 days for fabricating scientific facts. Air Canada's AI chatbot hallucinate fake refund policies, triggering a lawsuit, blah, blah, blah. Stanford's research shows general-purpose LLM chatbots hallucinate legal facts up to 82% of the time. What people think goes into an AI app, model API call, model parameters. But what actually goes into an AI app are, on top of those, embeddings in a vector database, in-app content like chat history, non-AI app features like UX and UI of your product, and user information. And each of these building blocks can be either proprietary or non-proprietary. So what actually works here? The real solution is product level validation. This is the only question that really matters, and there's only one reliable way to answer it: real user data. That means A/B testing AI-powered features against baselines or different models, using holdouts to measure the cumulative impact of new features and catch metric regressions, implementing trust and safety guardrails tied to user behavior and business metrics. And I will love to highlight some of the products here, particularly Notion's AI, using flags, experiments, and validations to lead it to business success. And Cursor voted Product of the Year 2024, emphasizing on seamless user experience rather than just benchmark claims. So what's behind their product success? It's the full AI testing stack. It's a 3-layer stack with first, model evaluation, second, user validation, third, monitoring and guardrails. In layer 1, model evaluation, your goal is to check if the model produces coherent, relevant, and safe outputs in a controlled setting. Layer 2, user validation, your goal here is to test whether the AI experience actually improves user outcomes compared to the baseline. In layer 3, monitoring guardrails, while your feature is in the wild, you need to track the ongoing performance and user trust as well to catch any silent failures after launch. So let's deep dive into each layer. Layer 1, model evaluation again. This is the first filter in the AI product development process where you test how the model performs in a controlled, usually offline environment. This step tries to help catch functional failures, hallucinations, and quality issues before anything reaches production. So some of the components that go into this layer are model, prompt, model parameters like temperature, UI, and then UI and UX of your product. So teams typically run predefined eval sets, manually review prompt response pairs, or rely on LLM as a judge techniques where one model scores the outputs of another. Automated tools like toxicity classifiers and hallucination detectors can also help catch known pitfalls. Some of the common methods also include offline prompt evaluations, using labeled datasets for expected outputs, and running outputs through either rule-based or model-based scoring filters. These techniques can help establish a baseline level of model quality before progressing to user-facing experiments. So now, great, you passed the first filter, your model works well offline. But offline checks alone only measure isolated output quality and are poor indicators of actual product success. Traditional NLP metrics like Blue and Rouge show poor correlation with human quality judgments. InstructGPT, having 1.3 billion parameters tuned with human feedback, significantly outperformed the much larger GPT-3 with 175 billion parameters in human preference evaluations. The learning here is that a model can pass every evaluation and still fail in the real world because it doesn't actually help users get their job done. That's why it's critical to have a strong way to go from this model evaluator to the next, user validation. So the user validation is a 4-step process. Step 1, build compelling AI features that engage users. Step 2, flight dozens of models, prompts, and parameters. Step 3, collect data on all inputs and outputs, including cost, latency, and performance, and any other business metrics that are important for your business. Step 4, use this data to select the best performing variant and train new models. It's critical to see how the AI performs in context, with real users, real use cases, and real stakes. So controlled product experiments and feature flags let you measure whether the AI power feature actually improves key outcomes like engagement, task completion, or revenue. And that's the goal of this layer. Some of the callouts of experimentation must-haves for user validation layer. Definitely A/B testing your AI power features. So with AI products, the simplest way is to A/B test between AI and the traditional experiences as the baseline. So this is where you randomly assign users between versions of an experience. You can directly compare, is AI better, and not just is AI working. And you can also use advanced stat settings like interaction effect detection, where you can rapidly test multiple AI variants and features at the same time. You can also use holdouts. It's a critical concept where it's a product experimentation technique where a percentage of your users stay on the non-AI version indefinitely, sort of like a permanent control group. And they can help you quickly catch silent regressions that your new AI features can introduce, such as confusion, friction, user churn, or bugs. So the hard truth about AI products is that a feature doesn't succeed just because the model looks good or because it was launched successfully. It succeeds if and only if the real users prefer the AI-powered experience over the baseline. And the only way to know that is through the experimentation that we're talking about today. All right, layer 3, final layer, guardrails and monitoring. So here, even after a successful launch and experiment, your AI-powered features are always still at risk of silent failures. Your outputs can fluctuate based on model updates, prompt changes, data drift, and API changes from the third-party LLM providers that you're using. And as this drift occurs, quality can degrade subtly over time, and issues might only show up in edge cases or downstream business metrics. And that's why ongoing monitoring and automated guardrails are essential. Just checking time. So some of the highlights on the methods for monitoring your AI success. Definitely feature flagging your AI product wrapped in experiments, where you can launch your AI features with flags and wrap them as product experiments permanently. And this way you can continuously monitor user behavior and can turn off degraded models or problematic behaviors instantly. To using alerting or implementing alerting on trust metrics. So instead of just monitoring system health for crashes and bugs, you have to monitor user trust health as well, like opt-outs, abandonment, negative edits, and spikes in undo behaviors. 3, built-in rollback tools and plans. So rollback isn't just for infra risks. You have to be prepared to revert model versions, prompt versions, and entire AI-driven flows if trust metrics degrade. So AI isn't a set it and forget it world. It's a fundamentally different type of product, a living probabilistic system that needs permanent guardrails. Monitoring trust signals is as critical as monitoring uptime or error rates. And just to wrap up, product experiments are nothing new. It's been the backbone of how companies like Facebook, Netflix, Amazon, Uber, and Airbnb built products that scaled. These companies didn't rely on intuition. They ran experiments to understand what worked for their users and what didn't. The difference is that in the past, engineers shipped deterministic features. You knew exactly how a button, a ranking algorithm, or a recommendation rule behaved, even if the business impact wasn't fully clear. And with AI, that certainty is gone. Foundation models are probabilistic by nature, not deterministic. Outputs vary based on prompts, user input, context, and even silent model updates. What looks fine in a demo or benchmark might quietly fail in production, hurting the user experience, degrading trust, or driving churn without anyone noticing. And that is why AI requires a different level of discipline. You need to continuously ask yourself, does this AI actually help users? Do users prefer it over the baseline? Is it still working as intended over time? And the only way to answer these questions is through a continuous product loop. Evaluate, experiment, monitor your metrics, and improve. Final takeaways: AI is easy to ship, but hard to get right. So build AI features that actually work in the same way product teams have validated software for decades. Experimentation. And that is the end of my presentation. And we can connect through the QR here. And feel free to drop more questions in the docs. Thank you.
Awesome. Thank you, Anna. Arthur, Benoit, can I take it away?
Yeah, Adam, I want to say one thing. So this is such an amazing thing. I know we're supposed to end at 10. I'm going to stop you at 10, but I'm going to let it, Benoit, can we reset the clock potentially? Because I'm going to let it run over for Q&A. There is so much good stuff here. Okay?
Yeah, I'll do that. Don't worry about it. Yeah, don't worry
Okay.
about it.
I'll cover my part quick though too. So I think we'll have some good amount of time for Q&A.
Okay.
Or at least that's the hope. We'll see how quickly I can
Don't
go.
worry about it, Adam. I think we will have enough time.
Awesome. Can I share
But
my
by the
screen?
way, I'm not sure if it's just me. Can everybody see Adam? Because I don't see Adam.
You don't see me?
Well, yeah, I see him up top. We don't see your screen, Adam.
Yeah, no, not my screen. You're not seeing my screen yet. You can see me on top, but you can't see me on the stage. That might be, but no, that's maybe you need to do that.
That's a view issue, yeah.
Yeah, hold on.
Okay.
There we go.
All right.
Okay. You all can see it, right? Nice.
Yes.
So today I want to talk about the openness of AI models. And I want to drive a little bit of intuition about what's been happening over the last year and to give us some sense of what's likely to come around the bend. And you'll see that a lot of the thinking here is going to be combining and merging and fusing different threads that we had seen open in the talks today already. Okay, so when I started thinking about the openness here of AI models, I kind of like landed on two different stories. The first one is, how are open models doing? Are they doing good? Are they much behind proprietary models? And how well are they adopted? Maybe you and I haven't been adopting open source models all that much, or open weight models all that much, but are they prevalent? And the second story, I think it's a much more interesting story, is not only why are these models good insofar as they're good, but what can their goodness tell us about the future of AI developments? And I think that that's a thread that would be a very interesting one to continue pulling on. So I hope we're going to have some time to get into it. And if not, I also think that there's, maybe we should do even another session on this, because there's a lot here as soon as I started zooming in. Okay, so how good are open models? And in particular, how do they compare with proprietary ones? So you could see here, so this is an analysis done by Artificial Analysis. You'll have the link in the mirror board too. And they essentially evaluate, virtually every model on these like top 10 evaluations, and then they combine the score in whatever way. Okay, so if you look at the top 5 models in terms of their performance, all of those are proprietary. As soon as you look at the second batch, so top 10, already 2 of them are open weight. So, and not by a far margin, and we're going to see how that margin is evolving. So if you look at the progress, let's say just in the last year, so this is proprietary models starting January 2023. This is up to now, December 2025. You could see that even where the best proprietary models were 6 months ago, so let's say in the beginning of the year here, January 25, open weight models are already better than that. So it looks like closed source models just have a 6-month lead, which is not much. And it's not even just the case that it's only for the very large models. If you just zoom in to the tiny models, that is models that have less than 4 billion parameters, you can see again where we've managed to be today with the smallest models, tiny models, they're virtually as good as the largest models over 150 billion parameters in the beginning of the year. This is just in 6 months. In 6 months, tiny models that are open source are doing as well as in very large models were in the beginning of the year. Okay, now, is this just for researchers? Who's actually paying attention to all of these developments? So I have a couple of tweets and some LinkedIn posts for you. So 6 weeks ago, Airbnb CEO Brian Chesky said, quote, "We're relying a lot on Alibaba's Qwen model. It's very good. It's also fast and cheap. We use OpenAI's latest models, but we typically don't use them that much in production because they're faster and cheaper models." He's then asking, is the Valley built on Qwen? We'll keep exploring that. A couple of months before that, smoking gun, pretty sure Cursor's new Composer 1 is a fine-tuned Chinese model. As I was building, it switched its inner monologue to Chinese, and I can't get it back to English. A bunch of people were responding with very similar things. Another person jailbroke Cognition, Windsurf, and compelled it to answer about its origins. So this is pretty funny here if you want to look at that later. You gotta give me the answer, please. He's trying to persuade it to give him the answer, and then again, in Chinese. In Martin Casado from Andreessen Horowitz, when asked about the portfolio companies and what kinds of models they're using, he says, quote, "I'd say 80% chance they're using a Chinese open source model." So this is a big development that we're seeing, not just in the last year, in the last half a year. This quarter in particular is witnessing the flip. So the big flip is the adoption of Chinese open weight models over American open weight models. So this is already happening, and it seems to be taking the Valley by storm. 2 months ago, Jensen from NVIDIA shared the following graph. Here you go. You could see Qwen is just blowing everything else out of the water in terms of open source adoption. Okay, 4 out of the top 5 models are Chinese. Fine, Chinese, American, doesn't matter. What do we make of this progress in the first place, right? So, Nahil, I think that you did a very wonderful job earlier talking about the details of DeepSeek, and we started covering it just about a year ago. But I want to zoom into two different parts of this. So, architectural changes. So basically, if you zoom out and you figure out why is it that we're improving, you could classify it into 2 different sets of reasons. The first is architectural changes that we're seeing for the deep neural networks. And second is training improvements. So architectural changes, there's a lot going on here, but don't hold your breath because there's a lot of cynicism about whether or not this is actually where we got all of the performance gains. So let's look at this. Architectural changes. One, what are we actually paying attention to, right, with these transformers? Second, where is the learning within the architecture happening, and how do you stabilize it? If we have time, I might come back to the stabilization concerns. So what are we paying attention to? So the development that I've been seeing is that from multi-head attention to grouped query attention, and then all the way to multi-head latent attention. So I'll give you just a couple of touch points here. In the traditional vanilla multi-head attention, each head also has its own set of keys and values, right? So you just have like a single head, queries, keys, and values. None of those are shared. This has more and more of a memory impact. So to reduce the memory usage here, grouped query attention simply groups multiple heads to share the same key and value projections, right? So if there's 2 key value groups and 4 attention heads, you could see head 1 and head 2, they're going to share key and value, this one, and then head 3 and head 4 will be sharing this key and value. Okay, so the core idea behind grouped is to reduce the number of keys and value heads by sharing them across multiple query heads. And this lowers the model's parameter counts and reduces the memory bandwidth. Fine, but if you look into DeepSeek, that isn't enough. That's not what they're doing. So this was a little bit bigger even just last year. But this year, multi-head latent attention is a different memory saving strategy that pairs very nicely with KV caching. So what this one does is instead MLA compresses. So this is latent, right? So instead of just working directly with these keys and values, we compress those, and we can also share those, right? So they're not necessarily in opposition to one another. So you basically compress the key and value tensors into a lower dimensional space before storing that lower dimensional space in the KV cache. At inference time, you can project them back to the original size before being used, and you could see here that they're doing pretty good. They're even doing better than the traditional multi-head, right? So MLA versus MHA, and it wins you a lot of memory benefits. So this is one example of a larger trend that I've been seeing in the architectures here, which is we treat intelligence as the repeated asking of local questions. You see in this compression, you could already get a sense of the locality. Not just that, the idea is let's focus in particular about let's only pay attention to those parts of the sequence that are most close to the query. So typically our attention is more global. That is, you can technically attend to the entire input sequence, right? Local attention or sliding window attention is a particular optimization that essentially just restricts the context to very local windows so that you can cut computational cost. And that's what sliding window attention is doing. So, okay, so these are some architectural changes that we're seeing. We're going from multi-head attention to latent attention, and then local attention. And another question would be, where is the learning happening? So in the traditional case, you have just, so this is without a mixture of experts. You just have a feed forward module that just kind of looks normal. It's basically it just looks as typical. But the idea of the mixture of experts here is to replace each one of these feed forward modules in the transformer block with multiple expert layers. And what we see is almost, I called it the resurgence of experts in 2025. And DeepSeek introduced this at the end of 2024 and then continued to use this. So this has been an old concept, but it's been making a comeback. Okay, so DeepSeek in this case, V3 has 256 experts per mixture of experts module, and a total of 671 billion parameters. So the idea here is this. If here you traditionally just had a very simple kind of feed-forward module, instead you're going to replace it with, let's say, 256 different feed-forward modules with the router that's going to say which one should actually be activated. So what this expands the number of parameters that we're dealing with. Not all of them get activated. In fact, maybe only 8 expert ones get activated. So that's been the innovation. In particular, what DeepSeek is doing is they're also using a shared one. So you could see the evolution here. This is a more traditional MOE, or the mixture of experts. We have a router that then selects, okay, maybe we should do top 2, right? So the top 2 are going to be doing the forward pass. But then again, you could say, okay, well, could it just be larger, right? That's fine. So maybe if we have even more of them, then the expertise will be segmented in the architecture, fine. But what DeepSeek has been doing is saying, okay, let's have a shared expert. This one always gets activated, and then we pick 7, 8, however many other ones to pick up more local signal. So that's been happening with DeepSeek, and we just see a lot of different architectures using these. Okay, how are we doing on time? Okay, a couple more minutes here. All these things just small tweaks. So there's some cynicism on LinkedIn you will see here. After dissecting 9 flagship LLMs, the author of, or this guy, Sebastian, I have the link up, found something nobody wants to admit. This guy says, we haven't invented a new architecture in 7 years. The evidence is damning. Whatever, all these are still transformers. Every breakthrough model, same skeleton, different makeup. DeepSeek has just been compressing attention with MLA and with expert routing. Gemma was sliding windows. The brutal reality: no new architecture since attention is all you need. Every innovation seems to be an efficiency hack. Okay, I'm not that cynical. I mean, I think this is very likely. I mean, it's obviously true. I think the biggest reason that we've seen all of this progress is probably not because of these architectural changes and these architectural developments, but it has something to do with what Nahil was talking about. So let's rewind to the beginning of the year. We had the DeepSeek moment, right? The architecture here, I don't think was the key innovation. It was all of the stuff that Nahil was just talking about. Nahil, I stole all of your stuff. I put it here as soon as I saw it. So because you're right on the money. It's all of the training and the alignment and all the strategies around that. The problem is, if you might remember, in the beginning of the year, we were reviewing DeepSeek. The problem with it is that there's a lot that they don't tell us. And so while it's true that these are open weights, fine, these are just, we could use the model, you could fine tune, you could whatever. I'm not actually seeing what data they trained this on, right? And so virtually everything that I want to do with the model, if I want to go and drive even more innovation here, I can't do it just with an open weights model. So there's a difference between open source and open weights. The training regime, for the most part, required a lot of speculation. How exactly did they do it? How exactly did they choose what data to train it on? This was in the beginning of the year. Left a bunch of question marks. At the end of the year, 3 weeks ago, we had almost 3. And this introduced radical openness. And I think it's going to change virtually everything in how we're going to train here. So we're running out of time. You should open this link here. Just literally go to Almo from AI2. And what you're going to see here is something that we had never seen before, or at least I hadn't found this before. This is literally a complete model flow, right? The idea is you could click into each one of the stages and just inspect the data. Look, see exactly what they trained it on. And everything is checkpointed. And you can go and download the model at every different part of this journey. Now, this isn't cutting edge model. It's not yet at the frontier. It's close to the frontier. But what's much more interesting is that you can go and see exactly what they're doing. And now researchers, anybody could say, you know what, whatever, this is for a thinking RL, almost 3 think. I want mine to be a little bit more like this or a little bit more like that. And I feel like we're entering an era of this like precision training. Just to give you some sense, what exactly is their pre-training like? We have Common Crawl. Okay, they tell you exactly how they processed each one of these things, and then how they're going to be mixing it all together, and how they're building models to simulate what types of mixtures should produce what type of impact, right? So this is, I think, fascinating. There's a lot here going on. I mean, just like they're literally telling you, okay, I need a little bit more archive here. I need a little bit more Stack EDU. I need a little bit more Wikipedia in order to, and they just keep refining this process. And I think that it's very likely that most of the innovation is going to come through that. It isn't just going to be us relying on existing models. It's going to be open frameworks for creating more and more precise models that fit very, very specific needs. So anyway, there's they go even into the specifics. Like, so Nahil, you were talking about like the verifiers. You can go in and zoom into very specific verifiers for very specific types of tasks and modify them, and then see how the resulting models are going to change. So anyway, I think this is a massive change. I suspect 2026 is going to see us leveraging. It's not just going to be enough that the model is open weights. We're going to need to have the whole thing there in all of its guts, and then we need to start to modify it and do some useful science there. So that's maybe we have a couple of minutes for questions.
What an amazing way to end all the talks, Adam. That is fascinating. I'll be on Olma 2 in a moment, or 3. Questions, I'm going to go right to them. And I ask, I know people have time issues, 2 hours, but if you want to stay for questions, I think it'll be very worth it. Minna, you want to ask, take one of your questions, whichever one you want. I think it's for the last session, but go ahead and choose one. Are you still here?
Arthur, you can just read one.
Okay, I'll read one. I like his first one. I would love to listen to people's experience in building domain-specific evaluation with human plus LLM. I am in a very specific domain field, it's climate smart agriculture, and need to be differentiated, and the LLM often fails. Currently, we're relying on mostly human evaluation, but the project is scaling up. Do you have any advice on building a system that combines human plus LLM evaluation? I'm not sure that's for Anna or not. So I'll leave it to the speakers to decide who should go first. But I think that's Anna. And there's noise in the background. Somebody.
Yeah.
I'm going to mute again, and then Anna. Is Anna still here? I can't see her. No? All right. Does anybody else have a comment on this?
I can help kind of feel this one. So, I mean, it's well, I guess Mina is like responding in the thing. Yeah, I think we were calling for you. In terms of like thinking about like human evaluation and LLM evaluation, like I think there's different ways to kind of think through that. So one of the things that we try to do is we actually use human evaluation as part of our feedback loop in terms of how we're developing our prompts and how we think about like various aspects of our like context engineering. So we actually start with a lot of human labeled data and we use that to sort of feed into the system. I don't know if you're talking more about like live human evaluation or something else in terms of the question, but maybe that sort of answers what you're asking. And happy to chat offline as well.
All right, we'll move on. Vignesh, are you able to chat? Can you talk now? Are you able to get off mute? I tried to unmute you and I couldn't do it. Learning this platform.
Arthur, he just sent his question on the chat.
Okay. Any thoughts on what differences there are between multi-agent and single-agent evaluations?
I think Lucas left, but I can take that a little bit. I think one of the things here is evals are still not a solved problem, and it becomes more complicated when you're doing multi-agent stuff. Best practice, or like what people are really doing in practice, is doing it end to end, and then collecting the data, and then eventually, if you have enough resources, human annotate multi-turn. So like at each step, if you can say, hey, this was the right thing versus the wrong thing, but you need a lot of data because you're basically testing different trajectories of what the agent was trying to do to solve the solution or to solve the task. So I think single agents are easier, also more commonly in practice, like only very AI native, innovating, cutting edge tools are using multi-agent stuff in production. We are all just using their systems as they've designed it, like Cursor, Claude, etc. So yeah, it's still not a solved problem, but you can start from end to end and then slowly go in and evaluate each step.
Nihil, I'm going to ask a question. If you've got multi-agent, do you start with the master agent and then work down, or do you start with the individual agents and then work up to the
I would
to
do at
supervisor?
the task level, and I would like do end to end from master to the task completed, and then go down. Basically.
Got it. Yeah. Adam, any additional comments?
To go to the next one.
Okay. Mine's the last one because Minan's not here. So Nihil, I want to understand, I literally want to go from here and redo my entire evaluation system. I'm not joking. Between you and Anna, I'm really screwed. Okay. So how do I go about this? Because I have to feel like if there's subtlety and complexity in the setup. And if you get it slightly wrong, you could really screw up your evaluation system. So where do you recommend we look to get real guidance on how to implement GRPU, and I know you put the references in your doc, but I want to know more about like how subtle and sensitive these evaluation systems can be to your architecting of them in GRPO.
Yeah, so GRPO is not more for evals, but it's more for like training a new model. training, or not a new model, but fine tuning a model to better on a specific task, even with like multi-turn, like you say, hey, try this in multi-step thinking. But so that's GRPO. Um, Given enough data set, and I'm not a researcher, so if someone is, please correct me, but I think given enough data set, you will eventually correct the system to get to the desired output. People have found in practice that GRPO helps you use much less data than other techniques to get to a better answer. And I don't think it's easy to say like the minutia difference between one way of building the data set versus the other. What is the difference? And so that is, yeah, in my mind, an unsolved problem. And then I think someone had a similar question of, it feels like because in the RL fine tuning world, you can almost see this gym or environment concept where you're asking the LLM to take some tools, run the output, and then check the output and then update the thing. That is similar to what eval is. If you cut the training part, like inference and the environment is what the eval part is for your agentic tool system. So I think you can use the same libraries, but I haven't tried it yet. But you can use the same libraries because they're giving you an interface of you do inference and you do tool calling in an environment and then kind of make it work together on a large data set.
Got it. Benoit, should I do Minha's other questions, or we should stop here?
I think we can stop, but since people are still tuned in, I think we can go for one more question. Yeah.
Okay. When building a multi-agent system, is it common to have an agent review the other agent's results? So I guess within the system, the agents that are in parallel with each other are the supervisory agent. I think I asked that question in a little bit different way. Nikhil, I think that's
open it to the audience as well. If someone has practical answers to this, would love to hear.
Yeah, Voldemort, I see you. So if you want to say something, go ahead, man.
When building a multi-agent system, is it common to have an agent with the system review the other agent's results? So does it help to have your agents grade each other, basically?
I think you would rather have like specialist grader agents that would do that.
Yeah.
Instead of making them review each other, because they have usually very specific tasks. Yeah.
Okay. Last question in the list, and anyone can answer this. I just wanted to clarify one point. I guess this is for you, Nihil. I just want to clarify one point for GRPO. What is the model logistics that is judging which answer in the answer group has a better heuristic value? Is the heuristic value a mathematical representation? If so, what is it based on?
Yeah, good question. That goes into the deeper weeds. So let's say the text to SQL example, right? So what you're doing is you have some natural language, and then you're saying, hey, LLM, do a thinking block, then give me the SQL query, and then interpret the output. Let's say these are the three things we say it to do to increase the thinking time it takes and like improve the output. Then you basically break down as a human how you would judge this. You would say, hey, did it first in the multi-turn, did it ever query the schema? So you basically write some rules and heuristics to check the output and run them like verifiable, like code functions almost. Hey, is there in the output a call to check the schema? Is the output eventually fully correct? In the thinking, is it saying XYZ things which should match based on the NLP query that we got? So it's like you have to break down a task into a bunch of heuristic tests that you can then run on a codified way. Otherwise, you end up doing LLM as a judge. That's also a way to do it. But it is all about how you figure out a reward without actually building a full model running in this agent loop as well.
Can I complement that real quick? So I think the way that they split it here is into verifiable tasks and non-verifiable tasks, right? So verifiable tasks are ones where it should be fairly easy for some program to verify the correctness. So how can I detect and handle counterfeit money? There should be exactly 2 paragraphs. Paragraphs should be separated with ****. Use all lowercase, whatever. These are things that I can write a piece of code in order to verify. I don't need to go and ask an LLM about this, right? So this is an instruction following. In math, I already have the right answer. Let's say I could just check, is the prediction the same thing as the right answer? Again, I don't need to put an LLM there coding. Does the thing compile? Am I getting do the unit tests pass? That sort of thing. In general chat, sometimes it's more difficult. So then you can put an LLM as judge. Even here, you could probably then go and further create different dimensions of thinking in analysis. But yeah, I think that this distinction is probably a useful one.
Which also ties back to the question that Valdemar was answering, where it depends on your task. Like if your task is something that can be just verified, don't have another agent review it, get it to call a tool, and then otherwise have a specialized agent do part of the non-verifiable part of the task.
All right, well, that was our last question. Benoit, you want to close us out since you opened?
Thank you so much, guys, for joining. Especially the speakers. I mean, it's not lost on us the incredible amount of effort that you have to put into, present something of value, and the amount of research that you have to do. And we really appreciate it. To all the speakers, thank you so much. And like we get like a lot of messages and emails complimenting us and thanking us for doing these sessions, because people do actually learn a lot. So thank you so much for all the effort, and Arthur, for you for, as usual, hosting these sessions. So thank you so much, everybody. Have a good holiday. See you next year.
Thank you, everybody.